Setting up a computational fluid dynamic problem, CFD, in FEniCS can be very daunting and quite difficult for a new user or someone who perhaps isn't commonly used to playing around with code. So here in this guide, I hope to simplify the process of firstly creating a mesh, dragging it into a format which can be used by FEniCS, and then running computational fluid dynamics on it and getting our results and viewing them in ParaView. So to begin, we need to create this mesh, and creating this mesh can be done in a variety of software for computer-aided design. One of the ones I personally use is AutoDesk Fusion, and that's partly because I learn on Autodesk Inventor, and Autodesk Fusion it's free for hobbyists and creatives to use, and it has a lot of similarities to Autodesk Inventor, but there's certainly a lot of different open source and free versions, so whichever bit of software you're personally happy with, just make sure it exports as a .step file. And that I found a .step file is a lot better than some of the other formats such as STL for creating a mesh, as it seems to simplify the structure which a mesh is generated from, whereas an STL can sometimes have a few quirks, shall we say, when you're converting it to a mesh for FEniCS. Firstly, when we set up a document in a computer-aided design software, we need to make sure it's set to millimeters. And we could set it down to microns, which we commonly use for our microfluidic, but I found setting it to millimeters helps if you perhaps use this software for 3D printing, and it just simplifies the entire process. And previously, when I was working my PhD and my postdoctorate position, we were doing it in millimeters so that we can take our computer-aided designs and 3D print them, but also take these 3D models in the software and take them into a computational fluid dynamics software. Once the software is set up, we're just going to create a very simple curve channel. We're going to do this by making a 500 micron line, so half a mil, and then we're going to draw a circle with a diameter of 20 millimeters. And this is so that we can get a lovely arch for our curve. And this is to model something which you may have seen in my previous video for the inertia separation microfluidics. So that initial spiral, that initial curve. And the way we do that is just again by creating that initial circle, which is 20 millimeters, and then a slightly larger one, and then we just cap them off halfway around, and that is the 2D sketch done. And once we're done with the 2D sketch, we can then extrude it into 3D by 200 microns, so we get this lovely flat 500 by 200 micron square, and then this large 3D object which we can manipulate. And then once we've done that, as I mentioned before, we want to export it as a .step file. Exporting it as a .step file can depend on whichever software you use, but often there's just a lovely load of export properties or file types as well, and we just want to leave pretty much everything as default and just export it as that .step. Once we've exported as a .step, we want to import it into GMESH. And this is where it gets a little bit confusing, because once we get our model in GMESH, it will generally create this file called a .geo, and a .geo is essentially all the operations you perform to your .step file to convert it into that mesh. And of importance, we want to make sure that we have labeled our physical labels for our surfaces and volume. If we're doing this in 2D, it would be our lines and surfaces. But for this demo, we're just going to focus on 3D. So the way we do that is firstly open our .step within GMESH. And before we touch anything else, we want to make sure that we set our mesh maximum size to 0.03. And the reason we want to set it to that, and what that unit even means, is this is the relative unit to the mesh. So a 1 on this maximum mesh element size will correspond to 1 millimeter. And we want to set it to about 10 micron to 30 micron tetrahedrals or triangles for our 2D and 3D mesh respectively. And the next part, as I mentioned before about creating that geo, we must label our surfaces and volume. So the way we do that is with the simple tool on the left hand side of the panel here, select down through the menus to get to those physical groups, and then we must label every single surface. So in this case there's only 6 because it's essentially a rectangle box, but obviously curved around. And then we want to label our one volume, which is for that entire model. So things can get a little bit more complicated though when you want to do something which is called a structured mesh. So at the moment we're working towards an unstructured mesh, where the elements will just be filled in what is supposedly, well, which is the most efficient way possible for the software to fill our mesh. But we can actually control how structured our mesh is using a feature called transfinite. And transfinite allows us to add squares and blocks in a very controlled manner. And that's very important when we come to consider different CFD or computational fluid dynamics problems. The reason why we might want to do a structured mesh versus an unstructured mesh is because we're looking at a certain type of dynamic, or we want to reduce the amount of elements in our mesh and make them more efficient towards the dynamics we're trying to see. But again, anything we do here, and the same with all computational fluid dynamic problems, the parameters in the mesh we put in will ultimately affect the dynamics we pull out of the system. So I put this in as just here's how to do a structured mesh, but you're more than able to get the similar dynamics using an unstructured mesh. So the way we make it structured is by using the transfinite menu. This time we need to label our lines, and this is because we need to say how many blocks, how many tetrahedrals, how many triangles do we want on each line. And because this is again just a rectangle essentially, we want to label top and bottom of this rectangle with the same number of elements, and similarly we want to label the left and right parts of these rectangles with the same elements too. And then we can label the curves with the same elements as well. So we should approximately have 4 lines for each set of these parameters. And here I chose 10 for the left and right, 20 for the top and bottom, and I set 400 for those curves. One last thing we need to do with transfinite is label the surfaces again, similar to how we did it for the unstructured mesh. And then we need to label our volume, and that's similar to how we did it before, where we have to label the volume, so that we can generate that 3D structure and export all of the elements we need. For a unstructured mesh, we only need to label the surfaces and volume. That's the only parts we need to convert into our FEniCS mesh. Whereas for the transfinite, we must label the curves so that we can generate the surfaces, and then the surfaces so we can generate that volume. If we don't do it in that order, then we will likely result in part of the mesh being unstructured, or the 3D volume of it being a unstructured mesh, which somewhat defeats the object of using transfinite and a structured mesh. Once we've done that and we're happy with the mesh we've created, then we can go to export, similar to how we did in our computer-aided design software, and to export the format as GMESH. And in this case we want to make sure that these are GMESH ASCII. It doesn't matter necessarily which version we use, so we could use version 2 or 4 of GMESH, but it has to be an ASCII format. If we use binary, it will not work in the next stage and you will have to redo it. But fortunately, because of the way GMESH works, you've created a .geo format, so then you can quickly regenerate all the parameters for that mesh, and then you can just change that mesh size and density according to the CFD model you're running at. Once we've got the GMESH format, we can use this script by MeshIO. Using this script by MeshIO, we can take our GMESH format as either a 2D or 3D, and again 3D in this case, take out the parts we're interested in, which is those surfaces and that volume, and convert them into a FEniCS mesh. And the importance here before of labeling those physical labels is so that when we come to this FEniCS step and produce this .xdmf file, we have the labels so that we can use them within FEniCS to assign our inlets and outlets and our boundary conditions and any other conditions we may need to set. To confirm what our physical labels are, because we could record them down when we're doing our GMESH, but sometimes they can be reconfigured as we export our files, or as we export our mesh, is by opening them in ParaView. So by opening them in ParaView, we can view our labels for each boundary. So by viewing the labels in each boundary, we can clearly see here that a outlet is 18 and our inlet is 13, and then we can assign the rest of those labels to being our wall condition, so a non-slip condition in this case. As mentioned with those physical labels, we can now jump straight into this problem code, and whilst it looks quite daunting, the only part of this code we really need to focus on is these parameters in this section here. And of importance, we want to set the boundary facet, so physical labels we mentioned earlier, the import mesh, that we are importing from a mesh, we're not creating one within FEniCS. We also want to set our scale factor, because as I mentioned before, this is currently in millimeters, but the software, when it imports this mesh, assumes it's in meters, so we need to scale it down. We also need to say what our mesh file is, so where our mesh is located, as well as provide the subdomain file, which again is to use for those boundary conditions. As our problem is just going to be Navier-Stokes, we need to make sure Navier-Stokes is true, so it's enabled. So we want to use the basic incremental solver. This is something which I've spoken about previously in understanding the Navier-Stokes solvers, which you can click in the description below to read more and see more about the different ones that are implemented in this software. And we want to create a folder to store our results. So in this case, we just created a folder called results_curve channel. The other things we need to consider is the time steps. And in this case, we're implementing the CFL condition, which is the Courant, Fredericks, Louis CFL condition. And essentially this will calculate the optimal time step based on our mesh maximum size and the flow rate we're going to be using going into this mesh. And again, more can be read in a previous video I've done before. So in this software, we just want to put a dummy time step in. In this case, we just put 4e⁻⁶ for seconds. We set the start time as 0, so that's just when we'll start. That doesn't need to be changed. And we set t to 300. So that isn't 300 seconds, that is 300 steps, which it will calculate based on that CFL condition I mentioned before. For the inlet velocity, we have this expression which can calculate this lovely parabolic curve in 2D, and I've managed to implement it in a 3D fashion. So all we need to do here is provide an initial inlet velocity. In this case, we used 0.1 meters per second, and we need to define the dimensions of this model, which is 3D, so 3, and we have this condition called XYZ. And now this is important to define which orientation and which axes what we want to use for our coordinate system to assign our velocity values onto. In this case, it's set to 1, and 1 is for the XZ. So we're using the X and Z coordinates to calculate our Y velocity values. If the X is 50%, so in the middle, and our Z's 50% in the middle, we would expect it to be the maximum velocity. Whereas if it's on the edges and the corners of this imaginary rectangle inlet, we would expect them to be dropping off by 4 times the amount, as a basic parabolic curve suggests. So to run this CFD problem, all we need to do is open a terminal of Python or Python 3, depending on which one's installed on our system, source.py, which is our main source file for BERNAISE. Problem, so this is the problem which our file we've just been editing is called. So in this case, flow_curve channel. We just hit enter and we run. If we want to run this across multiple cores, or multiple CPU cores, which is recommended due to how intense and how time consuming these problems can be, you may want to use MPI run. Here we can define how many threads we want this to be spread across. In this example, we can use 4, and then that in theory will speed up our process by 4 times. But again, it's not a linear setting. It really depends on your CPU hardware restraints. So once we have ran our CFD problem, we can get the results. So the way we do this is going into that results directory we talked about and finding our U flow.xdmf. But generally that's what it's called, and we can just drag it into ParaView. Once we drag in ParaView, we want to make sure we hit apply so that we can see our mesh, and then we can start applying some really interesting filters, such as a cross section, so you can see across the Z-plane, so that you can see the streamlines and the flow dynamics. In this example, we do see some turbulence at the initial inlet, maybe due to instabilities in our solver, and become laminar across the model. And you're going further, we can start looking at applying streamlines to this, and we can look at applying further cross sections to the middle here. And because it's a curved channel and it's at the microscale and it's a laminar flow, we may be able to see some Dean drag forces. If you don't know what Dean drag forces are, have a watch of my inertia separation microfluidics part 1. But essentially here we're just going to apply a cross-sectional cut, and here we can then apply surface vectors only, because at the moment we're only seeing that flow which is going through our model. Once we've done that, we can then click apply and view those forces, because they'll be a lot slower because they are perpendicular to flow, they're not parallel, unlike the other filters we were just looking at. And we can apply glyphs, which are these small arrows, and we can see here that we are getting these Dean drag cycles occurring in our channel, which is really cool. And in case we want to take this and then apply it to different models, because we're changing our inlet velocity, we can save this as a state. And what this will mean is that we can change the underlying u.xdmf file, but keep all of those different filters we've just applied here. And by doing that, we can then load up a different model and load in those filters we've applied. And this saves a lot of time when we want to compare the cross-section of different models and compare the different speeds and velocities, which is super useful. And that's something which I did in my inertia separation part 1 video, just to give us those different cross-sectional values we see. Really, that's all you need to do to set up a basic problem within BERNAISE. It's a very powerful platform, and there's a lot of different things you can implement, and this is a very short, quick video to cover a lot of those different concepts. Of course, there's a lot more complicated models you can implement, and really the limitation of this software is the amount of CPU usage you have available. So if you only have a small amount of CPU power, you need to then consider using smaller mesh sizes and maybe running the problem for much less time, because it will take much longer to solve. Or maybe look at using a high performance computer cluster, perhaps at a local university or research institution, if you have access. Other than that, hopefully this helps and answers a lot of those basic initial questions on how do I run a CFD model within FEniCS BERNAISE. Any questions, drop a comment below, and if you like this, drop a like and please subscribe. Thanks for watching, see you next time.